Hello and welcome to the fifth topic in a series on artificial intelligence agents and AI in general that I've been recording over the past few days. Today, I thought we'd talk about search and, in particular, solving problems using search. It's one of the more pervasive parts of AI to the point that we really think of it in terms of searching for solutions to problems or searching for ways to learn. So search in general is an important part of AI and also important whenever we talk about problem solving agents. And as you recall from our previous conversations, an agent is a thing that has sensors of some sort that it's able to make observations about its reality, its environment, and then it's able to interact upon that environment in some way using some sort of actuator that changes the environment potentially, or at least the agent's location inside of that environment. So when we solve problems with agents, as the name would imply, we're looking for ways of finding answers to problems that exist in some domain, some environment, and so that's really what this is all about. So the idea of a problem solving agent is to look for a sequence of actions that enable it to reach a goal. And that sounds a lot like coming up with a plan, right? So recall, we've also talked about planning as the idea of coming up with a way to reach a goal. So you would use the combination of searching and planning to find a solution. Without information from the environment, an agent can't do any better than random. So it has to observe the environment. Otherwise, it's just rolling the dice and picking something to do. The four phases of problem solving break down into identifying the goal, problem formulation, so come up with a plan to reach it, search, look for multiple ways to reach the goal using within those constraints. So finding a solution and maybe multiple, and if there's more than one, then pick one, and you'll probably pick the best one or the first one, depending upon what's going on. Sometimes a solution is better than an optimal one that you haven't found yet, right? So, and then the last step is execution. So actually execute the selected solution to actually achieve the goal. We talk about open and closed loop. It's about when do you you ignore the precepts that you've been observing around the environment. So open loop, ignore the percepts, then breaks agent environment loop, assumes knowledge of environment is correct, assumes the environment doesn't change, and assumes the model is correct. Whereas a closed loop approach is going to monitor the percept during execution. It's safer than open loop. It enables adaptation and changing or correcting of incorrect assumptions. So they're design choices that you make, and you make them based upon the situation you're in. When we talk about search problems and solutions, there's an initial set of states. So you've got a set of states, which is your starting point, the goal state, which is the desired outcome. Actions are things that get information from initial to goal. And then transition model is a result of each action. So something happens as a result of the action. Then action cost function is a numeric quantity that's applied for taking an action. The path is a sequence of actions, and then the optimal solution is the lowest sum of action cost functions to reach your solution. And then the state sequence graph are states, states are nodes, and edges are actions. Sorry. So you've got nodes that are states, edges are actions or transitions between states, which is a normal way of modeling state transition diagrams. Abstraction is something we do a lot in AI, and it's applicable to software engineering and development in general. There's several forms of abstraction that we utilize in this particular scenario. Model, we may abstract mathematical or code construct, right? And a model is a simplistic abstraction of a real thing or some complex thing that you're trying to model or simulate or approximate, hence the term. It is a model of a real thing, if you will. Abstraction is removing details from the model and representation. You can think of it as zooming out, if you will. The level abstraction is the amount of detail, so think of it as zoom level. Valid represents the real thing, so it's a valid model. And a useful model is one that does so with less effort than the actual dealing with the real thing. So you're back to the whole point of a model is to create a simplistic representation of something that is more complex and is simpler to deal with. And at the time that it's more complex to deal with the model than it is the actual thing, then the model's not useful. Is the way to interpret that. So an example problem, and this is a classic problem from way back when. You probably don't see them as much now, but there was a time it was the thing. And it's a slider puzzle. The basic idea is that you have a 3x3 grid. Inside of it are numbered tiles that move around, and you may have a more complex one, as you see in the bottom left there, of 4x4. So 16 boxes. One of them is empty, if you will. It's actually not numbered, is more likely. Or it may be the hole in which you're moving things to, depending upon how it's implemented. So the basic idea is that you move it around to try to get them in sequence, and then so you can play the game, if you will, by sliding things around until you get one up into the upper left-hand corner, and then two, and then three, and then so on. And it's more interesting when you're sliding it around, you know, at your grandparents' house or something. Anyway, so when you're dealing with search algorithms, these are ways to find solutions. And so it returns a solution to a particular problem. That's the whole point of a search algorithm. Ways that we do that is sometimes we like to organize things into trees because trees have some very nice characteristics. There are no cycles or loops in them, being one of those. One of the challenges with searching is that you may end up in a situation where you're going in a loop. And when you do that, it throws everything off. Not to mention it makes it much harder because you have to then start working on detecting loops and have you been here before, that sort of stuff. If something's in a tree, you don't have to worry about it because you simply can't cycle. There's no edges that bring you back up. A node in the tree is a state in the search space. There is a child and a successor. Those are nodes that are either pointing, or a child would be one that is you're pointing to. So a node generated under a node. So it's a node with an edge pointing to it is the child. The parent is the node from which that edge originates. So the parent, as you can see, has the edge going to the child. And we see that over here, right? Parent pointing to a child with an edge as the pointing mechanism. Edges in the tree are actions that can change the state. And in this case, we're modeling these nodes as states. So the edge is something that changes the state. Expand a node is considering an action for a given state. And then you may generate a new node. So each possible state under a given state. So when there's legal moves, you may have some additional moves that become available because of a move you've made. In the frontier is that unexpanded, unvisited, unsearched set of nodes at the edge of the search tree. There's also the concept of a best first search. And so at each frontier, choose the path with the best local value. So you're picking of the stuff that you know at that particular point, the best local value. And then you have an evaluation function that's used to determine what best means, because we always have to have some way of scoring things with search like this. And then you do have a problem with this sort of approach, is that it may be susceptible to local minimum or maximum. And so you may not find the best solution. You may find one that is good, or it may actually be not all that good. It just looks like it when you're looking at it from that local minimum, local maximum sort of point of view. And only the states that you've not visited or with a lower cost function or cost are at the are added to the frontier. So there's very restricted things on what is at that frontier of your search. So when you deal with this, what do you need to do a search? There's certain data structures we often have to have. A node it's essentially just an object, if you will, that has a way of associating it with another node. You need to have a parent and a child, so there's direction to that association, and then oftentimes there is a cost associated with that state transition to go from one node to another. So the edges that are linking those together oftentimes have a property associated with them that is a cost. A frontier may be a queue. So it could be some sort of FIFO, LIFO stack or priority queue. So if it's got nodes in it, then you're not finished, right? So if it's empty, then there's no nodes in the queue. You're probably done, right? Or you haven't started, one of the two, depending upon how it's seeded. When you pop, you're removing nodes from the queue. When you top, you take a look at the top one. Don't pull it until you do that pop, and then push is in queuing something. So adding something to the queue, and that's basic queuing operations on whenever, regardless of what you're dealing with, the data structure, you're treating it as a queue. There may be redundant paths whenever we're dealing with searches. So the multiple ways to get from one to the goal state, they may even have the same value. There may also be cycles or a single loop or cycle. There may be longer loops or cycles where there's intermediate nodes in the mix, so intermediate state transitions. You need to know if to detect cycles, you've got to know where you've been before. So the previous visited states, you can, it's got to remember the past. So if it doesn't, it will repeat it. And graph search checks for redundant paths. Tree-like searches, you don't have to check because there's no way of having a cycle, right? Because you've removed them by converting it into a tree. Problem-solving performance. So how do you know if it's good? And there's at least several different ways of measuring performance, right? Completeness, will it find a solution if one exists? Report failure if there's not one. It may have to be systematic to be able to satisfy that, meaning it's an exhaustive search, literally trying all options. Cost optimality, will it find the lowest cost path? Time complexity, clock time, or state transitions that are involved to solve the problem. So how many nodes did it have to consider and edges did it have to traverse? Space complexity, how much memory is involved to do it, right? So lots of different ways of evaluating performance of a particular search. Uninformed searches, you don't really know much, as the name implies. You pretty much are going to search everywhere in a certain fashion. You may do breadth first, depth first, or some sort of bidirectional search. So, and these basically are not smart searches, right? They don't take into consideration anything that they know. They just kind of brute force their way through the tree or whatever structure is involved. So not a real good choice for things of any size. Breadth first, you visit each child before going deeper, right? So depth first, you're going to go deep as far as you can and then come back up. But there can be challenges because sometimes you can only go so deep, so you may have to introduce some sort of artificial limit that stops you at a certain point so that you don't have too big of a search tree involved. So informed searches, which is where it gets more interesting, which is using heuristics. So they will likely take advantage of the values that are being involved that they've learned about. So a greedy best first. So it looks for expand the lowest heuristic function first. And so the basic idea is that find the one that is the best and use it first and go down that path. An A star search considers the cost from the start of a node, essentially downward. Uses a priority queue as a way of doing that. Beam search is an A star search, or A star search is memory intensive, right? So as an alternative, we restrict the frontier, making it incomplete and suboptimal, but in doing so, having traded off the memory constraints or requirements of the other approaches. The right button, it'll be better. Depends on the only buttons. So heuristic functions, and a function is something that is basically takes into consideration some information to make a decision. So you basically evaluate the heuristic performance by considering the nodes generated an effective branching factor B star. So a branching factor, child nodes generated by a given node, and then the effective branching factor is a branching factor for a typical node. So it might be as simple as a mean. A heuristic that is always better dominates. So heuristics dominate. So this is just terminology of heuristics because we couldn't just say that it's good or better. Dominates. And pattern database split the problem into smaller parts that are simpler to solve. Pre-computation is the idea that you do some work ahead of time, calculate optimal paths in advance, store, and then reuse them. And you're basically doing some computation and storage ahead of time. And then you get it back as you have faster runs and cheaper results. And these are simple sort of concepts that you'll use in every part of technology. We oftentimes pre-compute solutions to decrease the time it takes to access the values. A good example being in some sort of an OLAP cube, as an example, the values are going to be pre-computed oftentimes to save some time. Materialized view being another example. You're taking something that would normally be evaluated at runtime and computing it ahead of time so that you can then not have to wait as long, right, when you need it. Some of this stuff is really simple whenever you start off, but then as you move into more complexity, it gets more interesting and challenging. We talked about searching in general as a way of finding solutions. Now we can talk about it in a more interesting environment. So as you move into complex environments. So we do have this problem, as we've talked a little bit about local searches. And a local search is only going to consider things within a relatively small domain or relative to the location of interest. You start from a state and you don't really keep track of necessarily how you got there. It's essentially kind of like a hill climbing or gradient descent, depending upon which way you're going. And it's used to solve optimization problems with an objective function. So again, objective function, a way of scoring how good or not so good you're doing. And then hill climbing or gradient descent as a way of going the way that's doing better. It's that simple, right? So there's basically, you keep track of the unexplored alternatives on the fringe and making sure that you by doing so, you're ensuring completeness. A local search improves a single option until you can't make it any better. So you can't, there's no more fringe to evaluate. And a new successor function is a local change, generally much faster and more efficient, but it may be incomplete. So the idea of hill climbing, it's a simple general idea. You start in some location, maybe down here or over here, and you start going in a way that keeps doing better. So wherever, repeat, move to the best neighboring state. If no neighbors are better than the current one, then you're done. So what happens if, what's bad about it, right? And what's good? So what's bad, you may find yourself in one of these local maximum or a flat maximum or a shoulder, and a shoulder is something that looks a good bit like a flat maximum, but there's actually, if you keep going long enough, it'll go back up. So whenever you're evaluating this stuff programmatically, you've got to think about, at a point, you've got this current state, this one little point in time that you know about. And all you know otherwise is that I came from someplace that wasn't as good. I'm going towards something that is better. You'll also, though, have to build in generally kind of logic that says, this isn't any better than it's been before, right? So I'm at a local maximum, and not just a local maximum, but I'm on this flat local maximum. So it's a plateau. And whenever you hit that plateau, you may not need to evaluate the entire level of that plateau to determine that this isn't a bad solution and you just stop. That may be the case. And also, by definition, we look for something better than our current state. Nothing will be better in a plateau. So you'll just keep going until you do hit the thing that is not just better, but worse. And so you may decide to stop earlier than that. But by evaluating some of these things, you may not know which is the thing you're dealing with. you may think you're at the global maximum, but you're really at a local maximum. And sometimes we'll do things with these sort of algorithms to kind of shake the table, right? So to get out of that spot and go to someplace else. We'll talk about that in a bit. So there's types of hill climbing, right? You have a greedy local search, so decisions made on a local condition. The steepest ascent, so find the path that's going up the most. A sideways move on a flat spot, keep going, hoping it's going to get that you're on a shoulder, not on a plateau. Stochastic hill climbing, choose uphill moves randomly. So throwing in some randomness and trying to find some place to go up. First choice hill climbing, generate randomly until a better choice is created. So look around until you find something better, and then random restart, pick an initial state until a goal is found. So start back over periodically and keeping track of the best ones you found so far. There's other approaches, simulated annealing, pick a random move. If a better result, result and accept, otherwise probabilistic acceptance of move, and then local beam search we've talked a little bit about previously, and then evolutionary algorithms such as evolutionary computing based upon Darwinism. So the idea of using some mutations and randomness to determine if things are getting better. So you basically take and essentially cross good and not so good until they get better, right? And this goes over this simulated annealing, and we'll skip over this in the genetic algorithm, basically showing the idea of, and this is a very useful algorithm or algorithmic approach that was very popular for a while, and then it's no longer popular, but it's still quite useful for certain domains. When you'll think about using genetic algorithms is whenever you're dealing with something that is a very complex system to simulate. So to come up with a model that is accurate in representation of that whole thing is really hard to do. You're probably in a place where you may want to think about genetic algorithms, just as a kind of a tip, if you will. So searching with non-deterministic actions. So we're starting to throw in some probabilities or belief. So belief state is a physical state that the agent thinks are possible. So these are the ones you think can exist. The conditional plan or contingency plan or strategy. This is a solution to the problem. So what an agent does depends upon observations during execution. So it's a plan, but with conditionality, right? So probability is mixed in. Actions have side effects or don't always work. So a robot vacuum may clean more than intended, or it may miss and not clean well at all. Sometimes self-driving cars sometimes drive on ice or slick roads. So the coefficient of traction is not going to be consistent. So leaps may be appropriate in these sort of situations. When you're searching in partially observable environments, you can't see the entire world, so you can only see where you've been, and it may change depending upon if the world is static or not. So there's no information about the world, sensorless or a conformant problem. Actions solve problems without sensing, so we may have to do this by taking advantage of the fact that our actions cause side effects. We do have some information about the world. So you start with a prediction of a unknown based on some belief state, compute the possible percepts that could be observed, and then update belief state based upon the percepts. So basically try to learn about the environment by using the fact that you will potentially produce side effects when you take actions. Whenever we're dealing with online search agents in unknown environments, so online search is something where you have the combination of compute and action, right? So offline, you compute a solution before you take any action. So before starting, you basically come up with what it is you think you're going to do. Whereas online would be you combine compute and actions. This is good in dynamic or semi-dynamic environments where things can change, situations where time computing has a penalty and may have dead ends. Sometimes you will hit a bottomless pit, if you will, at the end of a column or a alley or whatnot. So anyway, with that, thanks for listening. We've talked about search ad nauseum. It's one of the more important parts of AI. I hope you enjoyed it. And if so, like and subscribe. And if not, leave me some comments. Talk to you later.